Hi, welcome to this new video on drawing shear force and bending moment diagrams based on what approach? Differential relations based approach. In the last video, we have derived these two expressions, right? Which is d by dx equal to minus q of x and dm by dx equal to minus v of x, right? So based on just these two relations, we'll be able to construct the shear force diagram and bending moment diagram. All right. That's what we're going to see here. And apart from that, we have said the previous video that the sign convention, that is the positive sign convention, what we adopt for shear force and bending moment is as we see here, right? That is if the force to the right section, okay, of the beam is facing upwards, and accordingly, if the left section, the force which is at the left section faces downwards, we then consider that as a positive shear force. Similarly, the one which sacks the beam, right, is the positive bending moment that we consider. Fine. So we'll just have a quick recap here, okay, which will help us understand these two expressions. Then we will move forward. Now we have a beam here, okay, which is loaded by a typical loading, which is given by this Q of X here. And apart from that, we see that at both ends we have some concentrated forces and moments acting upon the beam. Okay. Now the question is how to draw the SFD and BMD. Fine. So we'll start with the SFD. Now, when we draw the SFD diagram, it has to obey this first rule. Okay. This rule says dv by dx equal to minus q of x. What does that mean? dv by dx, right? Which is what is usually dy by dx? We say this is the slope of the tangent drawn at a particular point, right? For the curve y of x. The same logic applies here, right? So here V indicates the variation of shear force. That is, in the shear force diagram, if we pick a particular point and if we draw the tangent at that point and if we measure the slope, that slope should be equal to the negative of load intensity in the actual beam, right? So that's what it says. So if we go by this idea, for instance, if I take a particular location along the span, say I'm taking this particular location, which is at a distance of x1 from the left end. Okay. Now, if I take this point and then if I draw a tangent to the shear force diagram, and if I measure the slope of this tangent, what should it be? It should be equal to dv by dx is the slope of the tangent at a particular point should be equal to negative of the load intensity at the same location, the actual beam, right? So at the same location, the actual beam, what is the load intensity? Load intensity is Q1, right? So therefore, this should be equal to minus Q1 at this location. That's what it says. Similarly, if you pick another point here, the slope of tangent drawn at this point should be equal to minus what is the intensity load intensity at this point? Q4, right? So therefore, it has to be minus Q4. That's why we see that we have drawn tangent at different points along the span of this particular beam, and we mark the slope of this tangent, which is equal to the negative of the low intensity at these typical locations. Okay. So if this has to happen, what should be the variation? The variation should be something like this. Okay. Because see, these slopes, what we measure here are all positive slopes. Okay. Only if the slope is positive, when we assign negative sign to it, it will indicate the load intensity which is pointing downwards here. Okay. So as per our convention, the loads which are acting upwards are positive. Okay. Only if we add a negative sign to this positive loads, it will mean a downward force, right? So that means only if the slopes are positive here, then if we add a negative sign to that, okay, we can read it out in a different manner also. I can write this as minus dv by dx equal to q of x as well, right? So in that sense, if we read it, then the negative value, I mean the negative sign added to the slope will mean also the respective ordinate of the loading diagram, right? So only if the slopes are positive, I can add a negative sign to that, okay, which means the load intensity at typical locations here, okay, which are pointing downwards, right? So I can't draw it like this. I don't want to go beyond this. This is well explained in the previous video as well, right? So in the same manner, one can also approach this bending moment diagram here. Okay. So here again, this variation is dictated by this particular expression dm by dx equal to minus v of x, which means the slope of tangent at a particular point in the bending moment diagram is equal to the negative of what? The negative of ordinate of the shear force diagram at the same location, right? So for instance, if I take the same location, which is this, right? I mean, at a distance x1 from the left end, if I draw a tangent here, and then if I measure the slope, what should it be? It should be equal to minus V1. Okay. At the same location, we need to go to the shear force diagram and see what is the ordinate. We should attach a negative sign to it, and that will be equal to the slope of the tangent at this location. Okay, that's what this expression says here. All right. So that's all. Overall, what we can say here is the ordinate of load intensity at a location equals negative of the slope of tangent drawn at the same location of shear force diagram. Okay, this is the first equation here. Second one says the ordinate of shear force diagram at a particular location equals negative of slope of tangent drawn at the same location of the bending moment diagram. Okay, so we need to find the variation such that these relations hold. That's all the overall idea is. In order to aid us in this regard, we are going to see some typical variations which we usually encounter. Okay, typical variations of loading, I mean. So, for example, we see this loading here, which is the uniform distributed load acting downwards. Now, this can be a load diagram or this can be even a shear force diagram. Okay, you can see it in both ways. Now, for example, if we consider a load diagram, then the shear force diagram should have a variation like this. Okay, why? Because only if this line is a straight line and faces upwards, then the positive constant slope measured here can be related to this downward acting force. Okay, because we see dv by dx equal to what? Minus dv by dx equal to q of x, right? So only if the slope is positive and then if we attach a negative sign to that, that will give me the intensity of load, which is also constant acting downwards. Okay, so there is a one-to-one correspondence here. The same manner you can understand all these figures here. Okay, you can quickly go through all these figures, right? Just if the loads are acting upward and if it's a UDL acting upwards, then the, for example, if this is a load diagram, then the shear force diagram should be something like this. Okay, only then the equations what we derived hold. Fine. So you see that if this is acting downwards, then this should be a positive slope. Okay, the vice versa also holds true. That means if the load is acting upwards, then this should have a negative slope. Okay, because we have a negative sign here, right, in these expressions. That's why it goes like that. Okay, one needs to be aware of that. Similarly, you can see in the next figure what we see here, there is a uniformly varying load. Okay, from left to right, which is increasing, but it is facing downward, right? Right, this faces downward. Then the, for example, if this is the shear force diagram, let's say, then the bending moment diagram should have this variation. That is, it has to vary like this in a non-linear manner, and then also the slope should be positive here. Why? Only if the slope is positive, then we can add a negative sign to that, and then we can relate it to the corresponding ordinate of the shear force diagram. Okay, if this is the bending moment diagram, right? So we can see that both should increase. That means if the ordinate of, say, the shear force is increasing, then the slope also should be increasing. But because of the negative sign what we had here, right, because of this negative signs, if this is increasing negatively, then slope should be increasing positively. Okay, so that's the same thing we can see in all these remaining diagrams. If this is positive, this is negative. Okay, if this is negative, this is positive. If this is positive, this is negative. But this trend should be same. Increase should, I mean, both should increase. or both should decrease. Okay, both should decrease or both should increase. Okay, so that's the overall logic here. Then if we are aware of this variation, then one can easily construct the shear force and bending diagram because it's straightforward, obeys. Okay, these diagrams obey these two variations. I mean, these two expressions. Okay, so you can relate it to this one or you can relate it to even this one. Okay, so these are given in general. Fine. I mean to say if this is the loading diagram, then the shear force diagram should be like this. Okay, on the other hand, say if this is the shear force diagram, then the bending moment diagram should have a variation like this. Okay, so it is applicable in either manner. That's what I would like to say here. Fine. And just to remind you once again that this is what we call positive slope and this is what we call negative slope. Okay, this also will be helpful in understanding these two expressions here. Fine. So that's all. Then apart from this, here in all these cases, we see a uniform variation of this load, right? The load intensity is uniformly varying, right? I mean to say there is no concentrated load considered anywhere here. Fine. But we also encounter concentrated loads, right? So if we come across a concentrated load like this, then there will be a jump in only the shear force diagram. Okay, only in shear force diagram. This has no influence on the bending moment diagram. I mean, at the same location, you can't see any variation of bending moment. Okay, so this kind of concentrated loads will cause a jump in the value of the shear force. Similarly, if there is a concentrated moment applied anywhere, then it doesn't have influence on the shear force diagram. However, you see a jump in the value of bending moment at that location. Okay, that's what we see here. That's all. These ideas should be sufficient, okay, not to construct a shear force, I mean, not to construct the shear force and minimum diagrams. Apart from this, what else one should have in their mind is this setting thumb rules, what I would say, okay. I mean, if we have any particular support, we can have external supports and internal supports, right? I mean, if we have a continuous beam, something like this, all right, let me say you have a roller here, okay, and you have a roller here, and say you have a pin support here. Now, this internal one is what I call internal roller. Okay. This extreme ones are what I call external supports. Fine. Now, if we have a external roller support at that location, the bending moment would be zero, but the shear force exists. Fine. The same is applicable with the pin support and a pin or a hinge support, right? If we have a external pin support, okay. So what happens there? The bending moment will be zero here, but the shear force will be present, right? So these things will be helpful in drawing SFD and BMD. Then what about a fixed support? In a fixed support, both shear force and bending moment will be non-zero, right? And what about a guided roller? The guided roller, shear force doesn't exist, but the bending moment will have a non-zero value at that location, right? And how about the internal roller? At the location of internal roller, both of them would be non-zero. Fine. So with this understanding, let us try to solve a simple problem. Here we have a simply supported beam with UDL acting on this location. I mean, for this span, okay, of the beam ABCD. Now let's start first with finding the reaction. In this case, it's easy. I'm starting with a symmetrically loaded beam. So both the reactions should be equal, right? And it should be equal to what? Half of the total load applied on this beam. So half of Q into 0.6L, you get 0.3 QL, right? So those are the values shown here. Now we need to draw the shear force diagram first of all. Now let's start with this left end. We already have said that whenever we have a concentrated load acting, there is going to be a jump at that location, and that jump's value is equal to the magnitude of load applied at this same location, right? That's why we see this as P. Similarly, in the minimum diagram, we have shown that the jump value is equal to M, the magnitude of the constant moment applied at that location. Okay, the same logic applies here. So we started with this. Okay, whose value is 0.3 QL, which is not mentioned here. Just consider that as well. And whether should it be downward or upward, we have said that this is the positive sign convention what we are adopting. That means if we consider the left hand, the force should be acting downwards in order to be considered as positive. However, we see that this force is acting upwards at the left and right. So therefore, we need to start drawing it in the negative direction, right? Now we have done that. When we move further from this end, we see that at no location here we have any other force acting. That means this should be remaining constant. Okay. Then what happens after this point B? Now we see that this UDL is beginning here, right? Now we have said that if we have a variation of a force, okay, acting downwards like this, what we need to do? This is what we have said, right? So if we have a UDL which is directed downwards, then the next diagram, which could be a shear force bending moment diagram, should have a variation like this, right? So that's what we are going to use here. Now we are seeing that as this force is acting downwards, which is also varying uniformly, then the shear force diagram should have a variation like this. Why? Only then if you find the slope, it's a positive slope here, it's a constant slope as well, then its negative value is equal to the intensity of, which is also constant here, right? Intensity of the UDL applied here. Okay, so this variation should be like this. So that's what happens for this span BC alone, right? So we start like this, then for span BC it should go like this, right? Now what happens after beyond this point C? See, beyond this point C, we don't have any load acting here, right? So therefore it has to remain constant here, right? Then the quick check what we can have here is, even though we are not showing the magnitude here, usually when you finish the diagram, here we are doing it qualitatively, but in case if you are using the values as well, okay, to be very sure, then we see that when we close the diagram, whatever value we get here should be equal to the reaction at that end, okay. So just we are doing it qualitatively, so I'm not getting into all that. That's all. That's how we draw the shear force diagram. So there is a one-to-one correspondence between the variation what we have here, okay, with the loads acting here on both portions such as AB, BC and CD. Fine. And also we see that when we consider the ND, now see we see a concentrated force acting here, right? So which is also acting upwards at this end. Any force acting upwards should be treated to be a positive shear force, right? That's why we also finish upward here with that particular value 0.3 QL. Okay. So that's it for about uh, drawing the SFD. Then now let's move on and then see how to draw the BMD, right? So this is not required as such, but anyway, for the sake of being complete, okay, I'm just showing it here. Now we have already considered the shear force diagram. Now dm by dx equal to what? Minus v, right? That is the slope of the bending moment diagram at, I mean, the slope of tangent at any point of the bending moment diagram is equal to negative of the ordinate of the shear force diagram at the same location, right? So that's the logic what we are going to apply here. Now we also know that what should be the variation for any particular variation of shear force, right? I mean to say here we have a downward force which is also constant here, right? So for that we can refer to this diagram here. See, for this, the next level of the diagram should have a variation like this, right? Now this is the variation of shear force diagram. Okay, so therefore this is going to be the bending moment, the variation of the bending moment diagram. That means if this is the shear force variation, the bending moment should vary like this. That's all the logic is, right? So that's what we're going to use here, as this portion is in this fashion. So the I mean, the bending moment diagram should have a variation like this. Okay, and mind that for signs what we are adopting, we are drawing the bending moment diagram on the compression side. Okay, not on the tension side. Just mind that. So that's what happens with this portion AB. How about now this portion BC? See here there are again see this portion in which there is a uniformly varying load acting downwards, and then this portion where there is uniformly varying load acting upwards. See, from here to here the intensity is decreasing, and then from here to here the intensity is increasing. Accordingly, we need to pick the respective diagrams. Okay, here now let's say we are considering this portion B. If I call this E, okay, midspan of the beam E. If we consider the span B, then we see that the force is acting downwards and the intensity is decreasing, right? So let's go back to this figure here. See here we have this, right? So the force is acting downwards and then the intensity of the load is decreasing, right? So now this is the shear force diagram. Then the bending moment diagram should have this variation, okay? So now the shear force diagram for this portion should be like this, right? So that's what we need to do here, fine? So for this portion, we are going to draw like this until we reach point E. Now, what about this portion EC? In this portion EC, we have force acting upward and the intensity is increasing, right? So we'll go back here. We are going to pick accordingly. See, here we have this wherein we have the forces acting upward and the intensity is increasing, right? So for that, the bending moment diagram should have a variation like this, right? So that's what we are going to pick here and put here, right? So for this portion EC, the variation should be like this. Okay, so overall we get the variation like this from A to C, the variation like this. Okay, mind this is a straight portion, whereas this is a non-linear portion. Okay, and finally for the span CD, we need to just see how this variation is. This is a upward force. Okay, and what else? This is a upward force, and then its intensity is constant. Now we go back here. We see that we have upward force and the intensity constant here. Okay, accordingly, the bending moment should have a variation like this. Okay, straight line. So that's how we should finish for this portion CD. Okay, so we have a straight line connecting C and D, and also mind that this both ends are simply supported ones, right? So I told that see, we have a pin support here and we have a roller support here. So whenever we have a pin support and roller support, what should happen? The bending moment should be zero, but the shear force, okay, will be non-zero. So that's why we see that at both ends here, the shear force is there. However, we see that the bending moment should be zero at both ends. That's all. Okay, so that's how we construct the bending moment diagram. Hope this video helps. We'll see a few more examples in the upcoming video. Thanks a lot for your patience.